of today's lecture will enable you to understand the reactions for the preparation of alkynes, reactivity of alkynes, and acidity of terminal alkynes. Let us start today's lecture with the preparation of alkynes. Alkynes can be prepared by the following methods. The first one is elimination reactions. Now student, the meaning of elimination reaction is that we are going to eliminate something from a compound in order to make alkynes. The second method is alkylation of sodium acetylide, but over here we are going to study the elimination reactions for the preparation of alkynes. Now students, let us start with the first method for the preparation of alkynes by elimination of hydrogen halide. Alkynes can be prepared by dehydrohalogenation of vicinal and geminal dihalides in the presence of alkaline reagents. Now what are vicinal dihalides? Which contains two halogen atoms on the adjacent carbon atoms. And upon elimination of hydrogen halide molecule, one after another in each step, it yields alkynes. Higher alkynes are also formed in the presence of alcoholic potassium hydroxide. Now you can see in the first step, a hydrogen atom from this carbon and bromine from the other is going to get eliminated to give vinyl bromide. In the second step, similar reaction is going to take place. A hydrogen from this carbon atom and bromine from the other is going to get eliminated, making a triple bond. Now students, let us look at the mechanism of this chemical reaction. For example, if we take hydroxyl as a base, it is going to abstract a proton from here, shifting this bond between carbon and hydrogen between these two carbon atoms, eliminating this bromine, giving vinyl bromide. In the second step, another molecule from the base is going to abstract the proton from the other carbon atom. And this bond between hydrogen and carbon is going to shift between these two carbon atoms, making a triple bond while eliminating this Br as Br negative. In this way, alkyne is formed. Now students, just like alkylated alkenes, alkylated alkynes are also stable. So in the presence of strong base like potassium hydroxide and at a high temperature, the triple bonds which are present at the terminal of any chain, it migrates in the center to give a di-substituted alkyne which is going to be more stable. Look at this chemical reaction in which rearrangement is not possible. Let us look why. You can see that this is a vicinal dihalide and on the either side two benzene rings are attached. So after the elimination of 2 moles of HBr from these two adjacent carbon atoms, it is going to yield an alkyne in which the migration of this triple bond is not possible. Why? Because of the presence of these benzene rings which are not going to allow any type of migration of this triple bond. So in such molecules, no rearrangement is possible. Now students, alkynes can also be prepared by reacting vicinal dihalides with sodium amide in the presence of liquid ammonia. Let us look at the chemical reaction. This is a vicinal dihalide when you are going to react it with 3 moles of sodium amide. Now why are we using 3 moles? Because in the first step, the amide is going to abstract this proton, shift the bond between these two carbon atoms, eliminating bromine in the mechanism we just studied. In the second step, another mole of sodium amide is going to abstract this proton, shift the bond over here, eliminating this Br and making a triple bond. Now why have we used 3 moles? The third mole of the base is going to abstract this proton, shift the carbon-hydrogen bond on this carbon atom as a negative charge. So, the negative charge on this carbon atom is going to attract the sodium ions that are present in the solution, and it is going to make sodium alkanide or sodium acetylide. Now students, this sodium alkanide are very important laboratory reagent, but they can also be hydrolyzed back into the respective alkyne. If we are going to use water, hydrogen is going to attach with this carbon atom, sodium with the hydroxyl group, making sodium hydroxide and yielding the respective alkyne. Now students, the second method that we are going to study for the preparation of alkyne is the elimination of hydrogen halide from a geminal dihalide. A dihalide containing two halogen atoms linked with the same carbon atom is called a geminal dihalide. When it is treated with a strong base, it gives alkynes. We are using sodium amide as a base in the presence of liquid ammonia. It is going to give us alkyne along with sodium bromide and ammonia. Now let us look at the mechanism of this chemical reaction and compare this mechanism with the mechanism that we studied for vicinal dihalides. Now students, amide acting as a base is going to abstract this proton, shifting the carbon-hydrogen bond between these two carbon atoms, making a double bond. By shifting this bond between these two carbon atoms is going to increase the valency of this carbon, making 5 bonds. So, in order to satisfy its valency, it is going to break down this carbon to bromine bond, and Br negative will be released into the medium. In this way, vinyl bromide is formed. In the second step, another molecule of base is going to abstract the proton from the same carbon atom. As you can see, this is the difference between geminal and vicinal mechanism. The bond between carbon and hydrogen is going to shift over here between these two carbon atoms, making a triple bond, and again release this bromide ion in order to satisfy the valency of this carbon atom, as it can make only 4 bonds. In this way, alkynes are prepared from geminal dihalides. Now students, after studying the methods for the preparation of alkynes, let us look at the reactivity of alkynes. Alkynes are unsaturated hydrocarbons, so they can give addition reactions in order to convert into saturated hydrocarbons. They also give substitution reactions due to the easy cleavage of CH bond. So, electrophilic substitution reactions are possible in the terminal alkynes. Now you can see that the CH bond of terminal alkynes, or you can say one alkyne, is polar. Why it is polar? Because the carbon atom of the triple bond is sp hybridized. And you know that sp hybridized carbon atom have a greater s character, hence greater electronegativity. Now students, all these factors make the terminal alkynes acidic in nature. Let us look at the salient features. In ethyne or other terminal alkynes like propyne, the hydrogen atom is bonded to a carbon atom, which is making a sigma bond by sp and s overlap, s orbital of the hydrogen and sp hybridized orbital of the carbon. The sp hybridized orbital have 50% s character, which renders the carbon atom to be more electronegative. This carbon atom of terminal alkyne pulls the electrons more strongly towards itself and make the CH bond polar. The partial positive charge of hydrogen atom is created, so this can be donated as a proton, just like the acids which donates the proton. It can be substituted with a metal atom. Now students, you can see that this carbon is sp hybridized, it is more electronegative. So it is going to pull the electronic density more towards itself, giving a partial negative charge to this carbon atom and partial positive charge to the hydrogen atom. Now any incoming base can abstract this proton, and the terminal alkyne is going to act as an acid and donate its proton. The bond between carbon and hydrogen is going to shift on this carbon atom as a negative charge, making a carb anion. Remember that we studied carbocation, a carbon carrying a positive charge. But over here you can see that there is a negative charge on the carbon atom, which is showing that terminal alkynes can donate their protons, showing acidic character. Students, let us study some reaction in which alkynes acts as acids. When one alkyne or ethyne, this is one alkyne or ethyne, is treated with sodium amide in the presence of liquid ammonia, or it is passed over molten sodium, alkanides or acetylides are obtained. The mechanism we have already studied. You can see over here sodium alkanide is formed, and in alkyne this is ethyne, which is having hydrogen atoms on either sides. So these two hydrogen atoms both have acidic character because they are directly attached to sp hybridized carbon atoms. So they are going to yield disodium acetylide. Sodium acetylides is very valuable reagent for chemical synthesis and is essentially ionic in nature. As you can see, the negative charge on non-metal carbon atom and positive charge on the metal atom, which is sodium. That is why it is ionic in nature. Now students, just like sodium acetylide, copper and silver acetylides can also be prepared by passing acetylene with the ammonical solution of silver nitrate or cuprous chloride. Silver and copper acetylides react with acids to regenerate the respective alkynes. Look at this chemical reaction. This is acetylene. When it is going to react with silver nitrate in the presence of ammonium hydroxide. This is called ammonical solution of silver nitrate. It is going to yield disilver acetylide or silver ethynide. White precipitates are going to form. Similarly, ammonical solution of cuprous chloride is going to react with ethine. It is going to give you dicopper acetylide or copper ethynide, which is going to give reddish brown precipitates. When we are going to treat these acetylides with any acid like sulfuric acid or nitric acid, it is going to yield the respective alkynes from which it is prepared. Students, let us start with the reactions of alkynes. Alkynes give addition reactions. Alkynes undergo addition reactions in an analogous fashion or similar fashion to those of alkenes, as both contains pi electrons. The high electron density of the pi bonds make them nucleophilic in nature, just like alkenes. There are two factors that influence the relative reactivity of alkynes as compared to alkenes. Those two factors are increased nucleophilicity of the starting pi system, that is the presence of triple bonds as compared to alkenes which have a double bond. Stability of any intermediate that is formed, for example, the carbocations that are formed, which you have already studied in Markovnikov's rule in alkenes, and we are going to study Markovnikov's rule in alkynes as well. The first reaction of alkynes that we have to study is hydrogenation, addition of hydrogen. Alkynes react with hydrogen gas in the presence of suitable catalysts like finely divided nickel, platinum or palladium. In the first step, alkenes are formed which then take up another molecule of hydrogen to form an alkyne. You can see in this equation, this is an alkyne. A hydrogen molecule is going to add across this triple bond in the presence of nickel as a catalyst, and you can see an ethene is formed. In the second step, another molecule of hydrogen is going to add across this double bond, and it is going to convert into a saturated hydrocarbon, ethane. Students, the next chemical reaction that we are going to study is stereospecific formation of a trans alkene. What is the meaning of stereospecific? Means over here the stereochemistry is conserved, that only trans alkene is formed, not the cis isomer. The reaction is a metal reduction, means addition of hydrogen is going to take place in the presence of a metal. The reaction type is addition, means hydrogens are going to add across the triple bond. Alkynes can be reduced to trans alkenes specifically using sodium in the presence of liquid ammonia. This reaction is stereospecific, giving only trans alkenes via anti-addition. Anti-addition means that the hydrogen atoms are going to add across the triple bond in opposite directions. The reaction proceeds via single electron transfer from sodium. Sodium over here is going to act as a carrier for electron transfer, with hydrogen coming from ammonia. The reaction conditions do not reduce alkenes. Hence, the product is alkene. Means after the formation of alkenes, no further reduction or addition of hydrogen is going to take place. The reaction stops at alkene and it is not converted into alkane by further reduction. Students, note that the stereochemistry of this reaction complements the catalytic hydrogenation, means addition of hydrogen. But over here, stereospecifically only trans alkene is formed. Now students, let us study the mechanism of this stereospecific anti-addition for the formation of trans alkenes. Now students, pay attention. This is an alkyne. Now this sodium acting as an electron carrier is going to transfer this electron to this carbon atom, breaking the pi bond in a homolytic fashion. The electron from the sodium and one of the electrons from the broken pi bond is going to make a negative charge on this carbon atom, a pair of electron. The second electron of the pi bond is going to reside on the next carbon atom as a radical. Now, you have to observe the positions of this negative charge, which is above this pi bond, and the radical is below this double bond. This negative charge is going to abstract a proton from ammonia, NH3. It is going to abstract this proton. NH bond is going to transfer on nitrogen as a negative charge. Now students, in the next step, another sodium radical is going to transfer another electron and is going to make a pair over here with the radical on this carbon atom, which was over here. And in this way, it is going to make a pair and a negative charge will reside on this carbon atom. Again, in the similar fashion, another molecule of ammonia is going to come and this negative charge is going to abstract another proton. Now look at the addition of hydrogen. One hydrogen was added above this double bond and the other hydrogen atom is added below this double bond. This addition is called anti-addition, means addition on the opposite sides. Now students, this is because of this homolytic cleavage and the positions of this negative charge and radical that the anti-addition is possible. Students, the next reaction that we are going to study is hydrohalogenation. Alkynes react with hydrogen chloride, hydrogen bromide to form dihaloalkenes. The reaction occurs in accordance with Markovnikov's rule. Remember that we studied Markovnikov's rule in alkenes. The second addition is according to Markovnikov's rule, because in the first step we are having an alkyne and it is a symmetrical molecule, and Markovnikov's rule only applies to unsymmetrical alkenes and an unsymmetrical reagent. But over here alkyne is a symmetrical molecule. So this H and Br is going to add across this triple bond and give us vinyl bromide. In the next step, now we are having an unsymmetrical alkene. It cannot be divided into two equal halves. And also we are having an unsymmetrical reagent. Markovnikov's rule says that the negative part of the reagent is going to attach to that carbon which is having less number of hydrogen atoms. So this carbon is having one hydrogen, the other one is having two hydrogen atoms. So the negative portion of this reagent, which is bromine, is going to add with this carbon atom. And you can see Br is attached with this carbon atom and hydrogen is added on this CH2 group, giving us 1,1 dibromoethane in accordance with the Markovnikov's addition. Students, the next reaction that we are going to study is hydration, addition of water. Water adds to acetylene in the presence of mercuric sulfate dissolved in sulfuric acid at 75 degrees centigrade. Now this is acetylene in the presence of water. Water is not going to add directly, but we need to add sulfuric acid and mercurous sulfate. It is going to give us vinyl alcohol. Now this vinyl alcohol is highly unstable, so it is going under rearrangement. Vinyl alcohol being unstable, why? Because it is having a hydroxyl group which is directly attached to the double bonded carbon atom. So it isomerized to give acetaldehyde in order to stabilize this structure. Except acetylene, all other alkynes gives ketones. This reaction is industrially important because aldehydes can be prepared by this method. Now students, this is the structure of vinyl alcohol. You can see that OH is directly attached to the carbon atom which is making a double bond. Internal rearrangement is going to take place. How? This bond between oxygen and hydrogen is going to transfer between oxygen and carbon, making a double bond. The pi bond between these two carbon atoms is going to transfer on this CH2 group as a negative charge. That negative charge is going to abstract this proton. In this way, an acetaldehyde is formed. CH3, C double bond O and H. Now, except acetylene, if we are having any other alkyne, it is going to give a ketone. Why? Because over here, instead of CH2, we are having CH3. So internal rearrangement of this alcohol is going to yield a ketone. Students, the next reaction that we are going to study is bromination. Chlorine and bromine add to the acetylenic triple bond in the presence of Lewis acid as a catalyst. The halogenation may be stopped at dihaloalkene stage. Why? Because the double bond of the dihaloalkene is less nucleophilic than the triple bond itself. Therefore, the reaction might stop at this stage. Now, what is going to happen in the first step? That bromine molecule is going to add across this triple bond and giving you 1,2-dibromopropene. In the next step, another molecule of Br2 might add and give you 1,1,2,2-tetrabromopropane. Similarly, this is another example. Students, we have studied the detailed mechanism for the ozonolysis of alkenes. In the similar fashion, alkynes also undergo ozonolysis. Ozone reacts with alkyne followed by aqueous workup to give 2 moles of carboxylic acid. Remember that in the ozonolysis of alkenes, we used to get a ketone or aldehydes, but ozonolysis of alkynes will give carboxylic acids. The mechanism is similar to that we studied in alkenes. Now students, it's time for you to think what are reducing agents that you are going to use to convert alkyne into cis-alkene stereospecifically and trans-alkene stereospecifically. In the topic we have already studied how to make stereospecific trans-alkene using sodium in the presence of liquid ammonia, which is going to give us trans-alkene. Now how to prepare cis-alkenes? Cis-alkenes are prepared by using Lindlar's catalyst. Now what is Lindlar's catalyst? It is platinum in the presence of barium sulfate poisoned with quinoline. It is stereospecifically going to give us cis-alkenes. Now students, think of this question, that is cis and trans isomerism possible in alkynes? If yes, what is